Hello and welcome to the 8th lecture in my operating system development lecture series. Today I would like to talk about the interrupt descriptor table. Now I think this is quite an interesting topic because at a certain point um, we have disabled interrupts. That is because by default interrupts are handled in the way that they are given to the BIOS in real mode, such that they can give back 16-bit opcodes which corresponds to some given BIOS operation. And that is generally very convenient. This allows us to ask the BIOS for certain services. However, right now, interrupts have a lot of will have a lot of different functionality, mainly used for either exceptions or peripherals and different extension cards, or even so-called traps, which I'll also be talking about. Yeah, so this is also pretty much the first table that it's really this thing that has to be done in the kernel. Bootloaders don't really do it, and I'm saying this because again, depending on the design of your operating system and depending on a lot of different factors, where the bootloader ends and where the kernel starts it may be ambiguous. So just like how I talked about implementing the GDT in the bootloader, but GDT is usually something that is put in the kernel. Um, but the reason for that is there was already a GDT in the bootloader because there must have been, because it's a requirement for protected mode or long mode. But the reason you re-implement it in a kernel is because, well, firstly, you want to know exactly what's in the GDT, you want to know all the selectors, all the data about the GDT, and, well, the second point is that you have full control over it. But the IDT and handling interrupts is something very typically kernel-ish, so I'm really excited to talk about it. So the interrupt descriptor table is it's a pretty simple structure. The goal of the IDT essentially is to specify so-called ISRs. So basically you have some interrupt. And as we know, an interrupt is this sort of signal that tells the CPU to stop whatever it's doing, handle that interrupt, and then go back to its state. So when we have an interrupt, we need some way of handling that, and this is done through something called an ISR. This stands for Interrupt Service Routine. So there's some routine, some procedure that, well, services the interrupt, as the name suggests. Basically, what do we want to do with the IDT is we want to tell precisely our CPU which interrupts, how should it react to those interrupts, to which ISRs that we define by ourselves, by the way, um, how should this mapping generally look, and it also specifies some extra data. So what is an IDT entry made up of? Um, well, this is, well, first, if it comes to implementation notes, you can implement this as C-struct, preferably with the attribute packed, meaning that they'll be next to each other in memory, and this is going to be guaranteed. Um, but if you're doing this in assembly or whatever, I mean, it doesn't matter as long as it's the same data, but it will be received by the same assembly instruction, LIDT, which is like LGDT. But I'll talk about that in this lecture. So, what is in an IDT entry, right? So we know that we have an ISR, an interrupt service routine, and this is actually going to be very vital. So we have our ISR, And obviously the ISR has some address, right? Now we are going to call that the offset. So the address of our ISR is going to be our offset. So this obviously makes sense because, well, this nomenclature is a result of the fact that whenever it will try to reference something in the interrupt service routine, it will not reference it, well, it will reference it through the whole address, but it doesn't care about the whole address initially. It has some values in terms of the ISR relative to the ISR, and it will have to offset them by the initial address of where it starts. So this nomenclature makes a lot of sense. So we have some ISR, we have some way of handling our interrupts, and one IDT entry looks like the following. First, we have 2 bytes, so 16 bits, that specify offset low. In other words, these are the youngest 2 bytes of our offset. I mean, this nomenclature is, it's just a nomenclature I've chosen. I wrote an underscore there because that's what it looks like in my code, but that doesn't matter. You can call it whatever you want. What matters is that the first 2 bytes of your IDT entry should be the youngest 2 bytes of the address of your interrupt service routine for that interrupt. And yeah, I think that should be pretty clear. So then you have 2 bytes. And this should be the selector of your GDT code segment, right? So you might remember that in your GDT, right, we had a code segment, we had a data segment. You potentially could have also defined a code and data segment for the user space, but it's a good thing to think about. And there must have been some offset at which the code segment, well, we're specifying everything for the kernel right now, so we care about the ring 0 code segment descriptor offset from the start of the GDT. This is usually going to be 8 or 16. So just take a look at your GDT, right? Or you might even remember where you put it, right? And either way, this is going to be your GDT code selector. So, for example, if you put the code descriptor right after the null segment, then right, the null segment is it is 8 bytes. We start indexing from 0, so we go 0, 1, 2, 3, 4, 5, 6, 7, and then the next one is going to be your code selector, obviously. Then we have 1 byte for something called the IST, or the interrupt stack table. So this is something usually specified by the TSS or test state segment. So this is used to handle stacks and different user space processes. We don't really have to care about this for our purposes, so this just could be 0. So then we have 1 byte of attributes. Now, this is usually set as a sort of magic number for the sort of attributes that you want. However, I would like to understand how the bytes is structured a bit more. So first, you have the present bit, which tells you whether this is even a valid IDT entry. And this, again, here we can actually see the significance of the present bit, because in earlier structures that I talked about, the present bit might have seemed sort of insignificant. But here we can clearly see, hey, we might have some interrupts that we don't want to set any ISRs for. And then you could always just not define the present attribute. And this immediately tells you, hey, I don't even have an ISR for this. Well, please don't treat it as an entry. So, oh yeah, and by the way, the number of the entry, right, it always corresponds to the number of the interrupt, right? Okay, so you have 256 unique interrupts on x86, and basically every IDT entry, the next following entry, is going to correspond to that interrupt number. Yeah, so the present bit, obviously, if you're actually going to define all of this and you're specifying the address of the ISR and everything, you're going to make this present. And then you have to specify the DPL, which stands for desired privilege level. So that's simply this concept of a ring, right? So again, we're in the kernel, we want maximum permissions, so we want ring 0. So we'll set the DPL to 0, 0. So this was also a thing in the GDT, so it shouldn't be troublesome. Then the next value is simply reserved, so it's going to be a 0. But then this is the first nibble. The other nibble is actually going to be the type, which is a bit more interesting. So essentially, there are two types of interrupts. Well, this isn't a fully correct thing to say, but there are two types of what you can handle with the ISR from an IDT entry. So what I mean by that is you have a type which is simply an interrupt, and just a standard interrupt that's 111 and then a 0. So this is an interrupt, and there's also something called a well, this is actually formally, I should say that there are two types of gates. And this is the proper nomenclature for this. So you have something called an interrupt gate, which would be a 111 and then a 0, but you also have something called a trap gate. Which is just all ones. So what is the difference between the two? Well, the interrupt gate is simply a full-on interrupt in the sense that, okay, we are sending some signal, and the CPU can't do anything right now but handle this signal. So we'll have to, and I will actually talk about it, we have to send something called an acknowledgement. And this will actually tell the CPU that, hey, you can actually do things now. And we'll also do IRET, right, which returns from an interrupt. So whenever you define an interrupt gate, this means that you're talking about an interrupt that completely interrupts the CPU, and there are going to be formal procedures to tell the CPU that it can even do things. A trap gate is sort of different. It's just a signal. Yes, it is a signal that tells the CPU to do something and to handle this thing. And you know, it can be this asynchronous mechanism in this. Well, it's not really asynchronous. What I mean by that is that at any moment the CPU can receive the signal, and it will have some handler for this. But it can still do other things and like handle other interrupts that might occur. Okay, yeah. So if it comes to traps, one potential use for them might be software interrupts, right? So I mentioned that processes in the user space communicate with the kernel using something called a system call. And the way that system calls are usually implemented is you have some interrupt, and this interrupt is performed, and then the kernel reads values of a different registers at the time of performing that interrupt and does some service. Sort of similar to how BIOS services work. For that, trap gates are actually very good because we have some way of, this is an interrupt in the sense that we're telling the CPU to do something about the signal and handle it in some sort of sense, which allows for a kernel to, which even allows, for us to use those ring 0 permissions of a kernel and do something, right? But for most of our purposes right now, we're just going to do a standard interrupt gate, not a trap gate. So this is just going to be 1110. Okay, and it's also standard to actually write this attributes byte as a hexadecimal value and to sort of treat it as a magic number. So let's convert it to hexadecimal, right? So we just convert nibble by nibble. This is going to be, 100, that's just 8. And this is just below the maximum, so just below F, so that's E. So you can set this to hexadecimal 8E, and this is going to be a proper attributes byte for most purposes. Okay. Then we specify 2 bytes again. And we are this time going to specify the offset mid. And so you can treat it, okay. So theoretically, what we actually want to specify here is 6 bytes of the rest of the offset. But I'll break it down into 2 smaller values, and the reason for this is this sort of practical perspective of, hey, you'll have to implement this, and most programming languages don't just allow you to have a 6-byte data type. So I'm going to split it up. But essentially, you're going to have 4 bytes of offset high, with the idea being the same. So over here, you want to specify the 2 youngest bytes of the ISR address. And then over here, you're going to specify the 2 bytes that are right after the 2 youngest bytes. And then the whole rest, so the whole, you could say, oldest part of the offset is then going to be contained in those 4 bytes. Yeah, that's just the whole idea of it. And to practically set those offsets to think about it, like what do you actually have to do, right? You're going to have the address of the ISR. Somehow, usually the ISRs will be defined in an assembly file, and then you'll extern those ISRs. And then once you extern this ISR, you have this unsigned long, or at least you'll convert it to an unsigned long, and you'll be setting those values. So you have that. See, it's a 64-bit value. It's comprised of 8 bytes, and you can simply AND it, right? Yeah, you can just use the AND operation and set all the. So, for example, if you want to get the 2 youngest bytes, right, then it should be pretty clear that you can just perform the AND operation, set the first 6 bytes to zeros, and then you just set the last 2 bytes to ones. And if you're going to do that, well then clearly you're going to only extract that, because only those bytes can meet the condition that 2 ones are going to be there simultaneously. And again, you just specify different ones and you move them in order to extract those different bytes. This shouldn't be that difficult. Okay, and then we have 4 bytes. of zeros. So this is just 0. So this is just like the null descriptor or something. We simply have to define 4 bytes of zeros. And this probably should be the simplest part. Okay, so let's sort of sum what do we have here. What is the size of one IDT entry? We have 8 bytes plus 4 plus 4 plus 2 plus 2 plus 2 plus 1 plus 1. So that's just 10, 12, 14. That's just 2. So we have 16. Okay. So as you can see, one IDT entry is 16 bytes. So this is 16 bytes. In other words, you might say that's 2 to the 4th bytes. And this is actually a pretty important piece of information, because we will want to. Okay, so we have our IDT entries, right? So you don't have to set every IDT entry. Most of them they can be 0 if you don't want to handle a given interrupt. So you create some ISRs, so you create some interrupt service routines, you extern them in a C file, or you could write all of this in assembly, doesn't matter, or you could use a completely different language. Again, this is all language independent. So then you just use the ISR, you extract all the offsets, you can set this to 8E, you set this to your GDT code selector, usually 8, you can set the IST to 0, and this is just going to be zeros, and you are supposed to create 256 of those entries because as I said, there are 256 unique interrupts. Okay. So we know that we have 2 to the 4th byte in one such entry, and I just said that we need 256 of those entries, which is 2 to the I, right? So we sum those and we get 2. We multiply those, so we sum their exponents and we get 2 to the 12th. Okay, and 2 to the 12th, as we know, is just 4096. Okay, great. So we have the number 4096. And this is going to be useful because we'll have to specify, just like with the GDT, where we had a GDTR, with the IDT, we have something called the IDTR, or the Interrupt Descriptor Table Register. And in the Interrupt Descriptor Table Register, we specify the 2 exact same pieces of data as in the GDTR. The size of this whole descriptor table, and we'll also have to specify the offsets. So where does begin? Where is our interrupt descriptor table in memory? So we already have our size, except just like with the GDTR, we assume that the IDT is non-empty. So we require for the IDT to at least have 1 byte. And in order to save space, right, 0 is mapped to 1, and 1 is mapped to 2, 2 is mapped to 3, and so on. So actually, if we want to define our size, then instead of writing 4096, we actually have to specify the size as 4095. So this is going to be the size, and it's the same as in a GDTR. I'm pretty sure it's just a word. So we just define a word. So that's our size, and the offset is going to be, well, wherever you place the first entry of your IDT. So again, this might be externed, and you might just get wherever you statically define the IDT or something, or you might have reserved the IDT some space using the linker, whatever. But it should be relatively easy to obtain using the technologies you use. the address of your IDT, and you're just going to place it there. Perhaps I'll get to, now I cannot draw an ampersand. I think that's close enough. Okay, so this is the address of your IDT, and that is very symbolic notation, by the way. Because realistically, if you're going to make an IDT as a huge array of IDT entries, then if you're using C, then you won't have to get the address because the IDT itself is already going to be the address of the first element of the array. Doesn't matter. Okay, so that's our size, that's our offset. We know that we have to specify the address of the ISR. We know everything that must be contained in such an IDT entry. Okay, so we simply have to define the IDTR. This is a D word, by the way. This is a word, this is a D word, so it's 16-bit, this is 32-bit. And again, just like with GDT, we have to use an LIDT instruction. We simply give it this dereference structure, and boom, we have loaded the IDT. And once we have the IDT loaded, well, usually, or at least this should be the case, that we have interrupts disabled. So we should enable those. And this can be done through the STI instruction, which I've talked about. It sets the interrupt flag, meaning that this flag, which is responsible for the fact if those interrupts are even enabled, or it is set to 1, so they are enabled. I have started on this, I don't know, by example. Okay, so this is the IDT itself. Now, if it comes to defining interrupt service routines, this will usually be a routine in an assembly file, and you'll, for example, have something like ISR 0, ISR 1, things like that, and they will correspond to the numbers of those interrupts in the IDT entries. So whenever you create an ISR, you must remember what an interrupt exactly is. It's something that a CPU has to handle, but it has to go back to its initial state. And you, as the programmer, are actually responsible for keeping the CPU in the same state that it was before and after the interrupt. And I've probably mentioned this, but the context of a CPU or its exact state can simply be represented by the current value of all of its registers. So usually the idea is that whenever you define an ISR in assembly, what you first do is you push all of the different CPU registers onto the stack. Obviously, you don't have to push all of them, only the ones that could be potentially modified. So for example, you don't have to push the control registers, because if your interrupt handler somehow managed to change the control registers, then that is already bad. That shouldn't happen by assumption. So you just push all the necessary registers onto the stack. All the standard ones like RAX, RBX, and so on, and then all the R1 or 2 or 3 registers, all that common stuff. Then it is very important to store the stack pointer, because the stack pointer may be modified as well. So what you usually do is you move into a register that is used for storing addresses. You move the address of the stack, which is stored in the RSP or stack pointer register, right? So you can use a register for storing addresses such as RDI. So you simply move to RDI, you move the value of RSP. And then after you're done with that, so you've pushed everything onto the stack and you've moved the RSP into the RDI so that you can store it. What you do is you can usually call some handler that is in a different language than assembly, because you probably don't want to write all of your interrupt handlers in assembly, because that can often be painful. So you can use a higher level language like C, and you simply define some handler there, and then you extend in your assembly file, and then you call it from your assembly file after in the ISR after you've done this and that. So over there, once you performed the handler. Oh, and by the way, since you pushed it onto the stack, the handler in C or any other language can use those register values that were there when the interrupt was called. That is just a note. But it will have its use cases that I will also talk about. Okay, but probably not in this lecture. But okay, so we have our interrupt handler, and after we've called it, we can now move to RSP our value of RDI, right? So we have stored the value in RDI, we have called our handler, put the value in from RSP back in, and well, no, we now move the value from RDI back to RSP, and then we pop all the values, obviously in reverse order that we've pushed them, because that's how the stack works. So we do all of that, and then we have to do an interrupt return, or IRET. So this is simply an assembly instruction, IRET, well, an x86 instruction to be exact, and assembly just provides an abstraction for it. So you simply do an IRET, or since you're probably in the longbow, you might want to do IRET Q. So the Q, it stands for a Q word, quadruple word, 64 bits, right? An IRET Q. Might be something that you have to use in longbow. Okay, so that's the idea of IDTs and ISRs. But before you go and write your first interrupt service routine, it is important to notice that handling interrupts is not just setting up an IDT. Okay, cool, you've mapped certain IDTs to ISRs, but there are interrupt controllers which we also have to deal with. So in one of my previous videos, I've actually mentioned that in most modern CPUs, you have a chip that is called the 8259A Programmable Interrupt Controller. And I said that what it does is it redirects those interrupts by default to the BIOS. And this isn't fully correct, because nowadays 8259 is a sort of legacy chip. It's not really used that much anymore. And this sort of chip that is currently used as this top chip is something called the APIC. So it's not just a PIC, it's not just a programmable interrupt controller, it's an advanced programmable interrupt controller. And this doesn't fully specify the device either. Because actually, you could say that there are two flavors of this advanced programmable interrupt controller. You have something called the LAPIC, or local advanced programmable interrupt controller, and this one it's very useful, for example, when you do multiprocessing, because, well, it's local to the CPU that you're using, and it has some cool features as well. But there's also another programmable interrupt controller that comes under the name of APIC, and this is something called the IO APIC, or Input-Output Advanced Programmable Interrupt Controller. And both of those are generally very cool solutions. And they are also sort of ambiguous, because again, they do they're not like 8259A, where they specify very concretely an exact chip used for this. They're just a general name for the mechanism and some basic abstractions. Yeah, so those are two very cool new solutions. However, since this lecture is primarily about the interrupt descriptor table, um, and the ideas in the advanced programmable interrupt controller, or rather its purpose and what it's used for, is fairly similar to the 8259, I decided to talk about the 8259. And, well, we're lucky because pretty much any advanced programmable interrupt controller, at least at the time of recording this, boots up in something actually called 8259A legacy mode, which is simply a mode that is supposed to emulate the working of the 8259A programmable interrupt controller. And therefore, we can just treat it as the 8259A, and we don't really have to worry about the fact that we're using a local advanced programmable interrupt controller or an input-output advanced programmable interrupt controller. So essentially, a programmable interrupt controller, as the name suggests, is a sort of chip that controls interrupts, and it decides how those interrupts should even be handled before it even considers performing the ISRs that are supposed to be done for those interrupts. And if it comes to the 8259A, it uses a master-slave architecture, and that means that there is the master PIC and there's a slave PIC. If it comes to so we will communicate with those with the master PIC and the slave PIC using the I/O bus, using the CPU bus communication that I've talked about in the previous lecture. So we should know what are the ports of the master PIC and the slave PIC. So as I've said, there is usually a command port, which is used for sending commands and specifying, for example, what data will be sent, and there is data, which is used for receiving receiving information from this chip, or giving it some data, usually related to a specified command. So the command port for the master PIC is in hexadecimal, because as I probably mentioned, these are usually written in hexadecimal. So this is just 20 in hexadecimal, and the data is 21. And the slave PIC is pretty similar. It has A0 and A1 for the command and data, respectively. Okay, so we have the master and the slave. So what sort of information should we send to those programmable interrupt controllers? So we will be doing something called remapping the PIC, which basically means that we'll again set up a map for how everything is going to work, and we'll especially focus on IRQs. So I said that there are those 256 unique interrupts and such. However, probably the most vital ones, well, it's sort of subjective to say most vital ones, but the ones from 0 to up to 15, so the first 16 interrupts, are actually mapped to something called IRQ channels. So your CPU has IRQ channels, or interrupt request channels. And these are the channels that are used for requesting different interrupt handling of peripherals or extension cards and things like that. And some even consider them a pretty important resource. And nowadays, all of that is done automatically. And well, usually there's also a controller that is just mapped to a couple IRQ channels, and it handles everything, so it's not a problem. Like, for example, with USB, right? You have a USB controller, and it might use some IRQ channels, and then all the devices communicate through the USB controller, so that's not a problem. However, back in the day, you had to configure all of that manually. So you would have to actually go into the BIOS setup, and often you would have collisions. So, for example, because there are standard codes for IRQ channels. For example, 0 should be the programmable interval timer. 1 should be the PS2 keyboard, right? So this is pretty standardized, but there are some IRQ channels which different devices or different extension cards might want to use. So, for example, let's say you would go into an older computer and you would have some network card, and you would have some, like, let's say Sound Blaster Live, and they would both want to use the IRQ channel number 4, right? So you have to specify, hey, this is not the IRQ channel that I want to use. So you'd have to change it in the BIOS so that there are no collisions. And this information might have also been required whenever installing drivers for said device or extension card. So IRQ channels are pretty important, and IRQs, so with interrupt requests, are very important to handle. Because a lot of those interfaces that are very important to communicate with will communicate through IRQ channels. So first, the first thing that we'll have to send to both the master and the slave is, hey, I want to reinitialize. So we'll send an initialization code. So the PICs will know that they have initialized, obviously, upon booting. However, we want to reinitialize them, and we want to input some new data, so we'll remap them, in the sense that we'll give it new maps, new ways to think about going from interrupt to something else. So, firstly, we'll have to send to both of the command ports 0x11, just hexadecimal 11. So this is something that we'll have to send for both the master and the slave. I'll just say that this is our command, because this is the only command I'll talk about, except for the acknowledgement, but the acknowledgement will be sort of in a different category. So our command that we have to send to both the master and the slave pick is going to be hexadecimal 11. Okay, so we send 11 to the command port and to the command port of both the master pick and the slave pick. Great. Now, what do we have to specify? Well, first we have to specify which IRQs will be handled by which programmable interrupt controller. So one programmable interrupt controller, so either the master or the slave, they can handle 8 IRQs at a time. So that's 8 IRQs. So the most standard way to manage this, and I think a very logical way, is to let the master have everything from 0 to 7, and then the slave will have 8 to 15. And that covers the 16 IRQ channels. Okay, yeah, so simply, well, we've chosen our command. We went to reinitialization, so now we will have to send some data. So I'll just say data, and I'll say what to send to the master, what to send to the slave. This is obviously just a bunch of proposed values that will work. Obviously, you can read the spec and modify it. So, okay, so to the master, we'll send 0, and this is going to mean handle the 8 IRQs that begin from 0. So to handle from 0 up to 7. So that's 8 IRQs. So then we have to tell the slave 8, which means, hey, you will handle the IRQs from 8 to 15. Then we will actually send 2 differing pieces of information, depending on the master and the slave. Okay, I think there might be... It's... okay, it's a thunderstorm. Whatever. I for a second I thought there might have been a power outage, but oh well. I'll try to finish this quickly. So to the master, we have to send the IRQ, because one of the IRQs of the master has to be reserved by the slave. That's why it's called the slave. It's on one of the IRQ channels of the master. That's why it's the slave. And you have to give that IRQ channel, but you actually have to. Oh, by the way, all of those ports and all of those very bytes, right? Where we keep on sending bytes. So we use the instruction. That's just a note. Okay, so we have to specify the slave IRQ, but it has to be shifted to the left. So the standard is that the slave is plugged into IRQ channel number 2. So 2 as a byte in binary, which is going to be like so. And we actually have to shift that one place to the left. So this is going to end up being this value, which when we convert it back to decimal, that's just 4. So we have to send 4 to the master, and then we have to send the slave something called cascade identity, which is going to be 2. Now, what do I mean by cascade? Well, what is the sort of cascade nature of the slave? Basically, so it's cascade in computer science, if you don't know, it's when you have this passage of information from sort of one device to another, or from one bus to another, and such. And basically, you need to understand that the master must be properly be able to handle IRQ channel number 2 if the slave wants to handle any of its interrupts. So many people actually do this mistake. Oh, I'll talk about masking soon, right? So you'll want to mask your IRQs that you don't need, so they don't actually bother you because you didn't have a handler for them. Some people, for example, want to use IRQ 12, which is the PS2 mouse. So a lot of people have trouble with the PS2 mouse. Why is my PS2 mouse not sending interrupts to my operating system? Why is that not happening? And what they did is they unmasked IRQ channel number 12, but they forgot that 12, as we defined, 8 from 15, that's a slave IRQ. So there can't be a cascade. So the slave will never be able to actually handle that interrupt. So if you unmask IRQ 12, that's not enough to handle the mouse because that belongs to the slave. You should also unmask IRQ number 2. If you unmask IRQ number 2, that is going to unmask the slave, and it's going to allow this cascade so that the slave will be able to handle its IRQ. Okay, and the last piece of information, but we have to specify to both the master and the slave, and this is going to be identical. It's just the number 1. And 1, it selects the mode, because actually the 8259A programmable interrupt controller wasn't strictly an x86 chip. It was made for a bunch of different CPUs. So we actually have to specify, hey, what CPU are we using? And 1 just guarantees that both the master and the slave are going to be in 8086 mode. Okay, yeah, so that's everything. So we've set up the master, we have set up the slave, and we have used this command. And now something that we have to do is that we have to deal with masking. So basically, masking is the act of making some interrupt just not go through. So they won't actually interrupt the CPU. Along those all those interrupts that I mentioned, there's a lot of them. There are so-called NMIs, or known non-maskable interrupts, and you can't do anything about them, and they'll never be masked. But all of the IRQ channels can be masked, and this is actually something that we want to do. So it's actually good to start up with all of the IRQs masked, and then we will only unmask the IRQs that we actually need. So how do we mask any of the IRQs? And this is very simple. We simply have to send it as a byte to those data ports. So we'll send, well, it's a byte, right? So it has 8 bits, and each one of those bits is simply going to correspond to the next IRQ channels which this given PIC controls. So let's say we wanted to now mask all of the interrupts. Well, that is simple. We simply have to send the value 2555 or 11111111 to the master. So this is going to mask all the IRQ channels from 0 to 7. And then we send 25571111111 to the slave. And that's how we mask everything. And it should be mentioned that the youngest bit corresponds to the smallest IRQ. So this bit corresponds to IRQ 0, this to IRQ 1, this to IRQ 2, and so on. So yeah, this is the master, and this is the slave. So this is going to correspond to 8, this is going to correspond to 9, and the last one is going to correspond to 15. I think the idea is clear. Okay, yeah, and you can create a very simple function to unmask or mask. In order to mask, you simply inb, so you take the byte that is currently there, and you see, is the IRQ lesser than 8? If yes, send it to the master, just with the flipped bit corresponding to the IRQ specified as a function parameter. And if it comes to the, if it's greater than 8, then you have to subtract 8 from it first, and then just send it to the slave in a similar way with this bit flipped. Or not flipped, just set to 1 or set to 0, depending on whether you're creating a function for masking or unmasking. But you simply send this to the data port, and that's it. So now anything you send to the data ports of the master or the slave are going to correspond to those masks. So initially, you can just send that as 255, or you can write it in hexadecimal if you want to be fancy, FF. And this is going to mask all of your IRQ channels of both the master and the slave. Okay, that is pretty much everything. So you can try just writing a simple ISR for the IRQ channel 0. So you make an ISR 0 and you make one IDT entry just with the ISR 0 that is going to be there, right? And ISR 0 is the programmable interval timer, so by default what it will do is it will just trigger an interrupt periodically. You don't actually have to make any sensible handler for it. What you could just do is acknowledge the interrupt, right? So in the ISR, again, you're going to push everything, you're going to move RSP to RDI, then you're going to call your handler, and after the handler, you're going to put the value from RDI back to RSP and pop everything, and then IRQ. And what does the handler itself do, right? So you call your C function, what is it going to do? And, well, you can make it display a letter or whatever, or you can make it debug print to the serial ports, or to the COM1 ports. You can do something like that, and you'll see that it actually does it periodically. And it will just go like that in the serial terminal. But you must remember that whenever your handler ends, you have to send both the master and the slave the acknowledgement. And the acknowledgement is actually a command, and it commands the master PIC and the slave PIC to simply acknowledge the fact that, hey, this interrupt has ended. I have finished handling this interrupt. I'm now just going to return to the CPU's initial state and IRQs. So acknowledgement, the code of the acknowledgement command is hexadecimal 20. So this is the acknowledgement, or so-called ACK. So at the end of your interrupt handler, you have to send the ACK to the master command port and the slave command port, and this is going to finish your interrupt. Okay, so that was pretty exciting. That is finally something very kernel-ish, handling well all of those interrupts. So this is everything I wanted to talk about in this video. To summarize, you have to make an interrupt descriptor table, which is going to map different interrupts to their ISRs, or interrupt service routines. And the one IDT entry, it should be pretty clear. You have to make an IDTR, which specifies the size and offset, and then the dereference IDTR should go in the IDT command, which is going to load that. And then you're just going to do STI to turn on interrupts again. And an ISR should push all the important registers to a stack. It should save the value of RSP to RDI. It should call a handler. The handler should send an ACK to the master and slave. And then you load the RDA back to RSP, you pop everything from the stack, and then you IRQ. You must remember that after setting up your IDT and loading your IDT before you actually start doing anything, you should also properly remap your PIC. Okay, and then after that, if you wrote a basic handler for ISR 0, so the IRQ channel 0, and everything has been mapped properly, and you made it, for example, debug print a letter, it should appear periodically in your serial terminal. Okay, so again, this is everything I wanted to talk about, and I managed to summarize it. I hope that everything was clear. If anything is unclear, please leave it in the comments. If you have anything else to say, I'm, again, very glad to hear it in the comments. Even if it's something negative, then I will always try to take it into consideration, even if it's written in a rude manner. I think that it might have something valuable to say. But I can still take into account. So, I would just like to say thank you for the support on my last video. It really gained a lot of views, perhaps not for an average person, but for me it was definitely a lot, and I'm very glad that this series is really taking off. And I hope to see you in the next lecture, where I'll be talking about PS2 and other interfaces that may be used to communicate with peripherals and extension cards.